This is Mr. Cappert. We've been talking about statics, the study of forces on stationary objects, such as our truss bridges. Our truss bridges are not moving, so we've shown that you can sum all of the forces and set them equal to zero and solve for unknown forces. We have just one last part left to statics, and that's moments. This is a turning effect due to a force. It's also called torque. If you're somebody that's into cars and you hear the word torque, it's basically a rotational force. And there's a simple equation to find a moment. You simply take force times the distance at which it acts from your pivot. So the moment about this nut right here would be how much force you put on your wrench and then how far away perpendicularly that force is. Now, you want to use a bigger wrench to get off a very tight nut because as you increase the distance, the length of your wrench, for instance, the rotational force becomes greater. So this is why some people use what's called a cheater bar, where if they can't get a nut loose, they'll put a steel bar over the top of their wrench that extends out for several feet. So you're basically multiplying your rotational force. This is also why when you open a door, you want to press towards the outside. You want to press towards the handle area because you get the greatest turning effect for the amount of force you put in. If you push near the hinge, you'll notice you need a lot more force to open a door. So the first part, I want you guys to find moments. For instance, with this wrench here, find the moment of force produced by the following force being applied to a wrench. So you have 50 pounds of force being pressed down on a wrench. That's a lot of force. So that's somebody putting a lot of their body weight into removing this nut. So once again, for your moment equals force times distance. Your force is 50 pounds. It's being applied 2 feet away. That's your distance. And so 50 times 2 is 100 pound-feet for your units. So if you were to extend this handle, you'll notice that your moment would be greater, such as a 4-foot long wrench with 50 pounds would be 200 pound-feet. This is why you want to extend your wrench if you're having problems loosening a nut. Things are going to get a little more complex here. Hopefully you're not too scared. This is basically adding what we did before and adding in the new thing, moments. So you guys have already found support reactions at a point. So first step is you draw a free body diagram. We have this cantilever, they call it, that's stuck in a wall. Let's say somebody's pressing down with 10 pounds, somebody's pressing down with 1 pound. This 10-pound force is 2 feet away from point A. The 1 pound one would be 2 plus 1. It'd be 3 feet away from point A. So to draw a free body diagram, remember you remove all of the unnecessary things such as the wall. You want to draw this cantilever beam, the forces acting on it, how far away they are from this point A. And then this is going to be your moment. So this wall is holding the beam up. It's also holding it from going left and right, and it's also stopping it from spinning. Notice the reason they drew it going this way is because this 10-pound force wants to make this beam rotate clockwise. This 1 pound one wants to make it rotate clockwise. So what this is showing is that the wall is applying this moment counterclockwise to keep this from rotating. So I want you to find the support reactions. You've done that before. You want to first sum up the forces in the x direction. Let's make going to the right positive. So AX is the only force in the x direction. Set your x forces equal to 0, so you just get AX equals 0. So there's no force trying to pull this out of the wall or push it into the wall. So that's why this is 0 pounds. Just like before, sum up your forces in the y direction. Let's make going upwards positive. So you have negative 10 pounds because you have 10 pounds going downwards. That's negative. You also have 1 pound going downwards, that's negative. And the only thing going up is this support reaction, AY. The wall is holding up the beam. Set the forces equal to 0 because it's not moving. I then used algebra to solve for AY. If you need help with algebra, make sure to raise your hand and I can come over and help you. These two were a review of what we've done before for support reaction. This, starting right here, is new. So you are now going to sum up the moments about a point and set it equal to 0. It is not moving. It is not rotating. It's not spinning. So that's why it's equal to 0. It's stationary. So what this is saying is sum up all the moments about point A. So all of the moments. So you have 1, 2, and then a third moment. So the first force I said was 10 pounds. That's negative. I took it times the distance it is away from A. That's how you find a moment, force times distance. I also have 1 pound going downwards. That's why it's negative. And it is 3 feet away from the wall. So 1 pound times 3 feet. And then I have one more moment, and that is the support reaction of the wall. And it is going the positive direction. Set those equal to 0. I then used algebra to solve for my moment, this support moment, moment A. Now, something I forgot to say here is we always said the y direction is positive going upwards. The x direction is positive to the right. A moment counterclockwise is positive. You could inverse this if you wanted to, but I said anything going counterclockwise is positive. That's why I said MA was positive. It's going clockwise. These were negative because they're trying to make it spin clockwise, which I said was negative. You could flip that if you want to. Be sure to ask me questions. That's why I'm walking around the room. I'm looking for you guys to flag me down and ask for help.